Let's begin. So this lab would have been ideal to do a couple weeks ago, but we had the first week of class. We had no class on Monday, and then I can't remember if it was President's Day or Martin Luther King Day. Lost another Monday as well. So it would have been better to do this earlier. But with that being said, here we are. So we got a pretty simple lab for testing and verifying some of the concepts that we developed from transformers. And we're going to look a little bit at understanding the operation of a transformer, checking turns ratios, not only from a voltage perspective, but from a currents perspective. And then we're going to go ahead and look at and see if we can actually get some saturation characteristics. And if you can't remember, sorry, I've got bouncing back and forth. It's a little weird on the setup. But if you recall, what we have is when we do transformers, we can see that anytime we use magnetic materials, we tend to saturate a little bit. And the reason why that is a concern, or maybe it's not a concern, is because saturating an iron is not that big of a deal like it is if we were to saturate, if you could, a current carrying conductor. So a current carrying conductor, you can heat up very quickly. You get lots of inefficiencies, and it can become a problem. In magnetics, you're not consuming any real energy per se. So the consumption of that magnetic energy doesn't really cause you any problems because you're not losing any joules at that point. So most magnetic systems operate to some degree of saturation. And we're going to see that in this case, even with the transformers that we have, we're going to start to see some saturation of those transformers. So essentially, you're going to try to replicate this curve here. Okay, that's the third part of the lab, if you will. All right, so the first part of the lab is to build this circuit. I will append a little bit. This terminal here is going to be terminal 4. And then this you can pick, we're getting pretty good at it. This is red and black, red and black, red and black. And then the transformer terminals are all going to be open. And the reason why they're going to be open is we're just looking at the turns ratios. So if we can flip over to, I have to share a different screen. So if I can hopefully zoom way in, you'll be able to see. Let's see if this is zoomed in enough. If you look, can you all see the nameplate? I can zoom in a little more. Maybe this will be a wee bit better for us. So you can see that for a nominal 120 volt voltage, that's the rating of the winding between terminals 1 and 2. We have two separate, completely distinct sets of windings. There's a set of windings between terminals 3 and 4 and between 5 and 6. Now, does anybody want to guess what terminal 7 or terminal 8 or terminal 9 are? What do you think those represent? Those are physical terminals you can access.
Those are taps for different voltages, aren't they?
Exactly. That's exactly right, Arthur. Thank you. So over here, you have no tap. Over from 3 to 4, if you don't want 104 plus 76 plus 28, if you only wanted 104 volts, you could run wires between terminals 3 and 7, and then you could get around 104 volts when you plug in 120 volts. And so this is the same application when we talked about our home, where we have the primary would normally be like a 70 to 100 volts. And then the secondary would probably be more like over here, where you'd have a nominal 240 across the entire winding. But then you have a tap in the center that you can actually pick up half the voltage between either polarity. So over here, I get plus to minus here, 60 volts, and I get another plus to minus 60 volts here. So when I go across this winding, I get the full 120 volt. And so we're basically going to run 120, and we're going to check to see if we get 104, 76, 28, 60, 60. And we're going to check those with our voltages. So let's back up here so we don't have quite the zoom in.
Paul?
Yes.
So in residential, the center tap, isn't that the neutral?
Correct. But it's interesting though, when you say, and you're correct, the center tap is the neutral. It actually, if you wanted to be 100% correct in how you say it, the transformer has a center tap. It is connected to neutral. Okay, so the neutral is just is a point that we designate between two locations. And then we call that the actual center tap. So from the perspective of the transformer, it is tapped at the center, and it just happens to be neutral because we tie it to ground going into our house, essentially. Okay. All right, so you should go ahead and have a configuration like this, because this is all you're going to need to do this lab, 3 modules. And remember, I'm going to go ahead and energize the DAC, so you can see that the power supply is not configured. So I'm going to go ahead. Well, the DAC is not configured, so I'm going to run that over here. And turn this on, and now my data acquisition device should be good to go. And I just run this cable way out of the way.
I'm still just seeing your Word document.
Yeah,
I'm not
Oh,
seeing
let
if
me
you're
see
trying
if
to
I
show us a
share.
sim.
I thought I had shared the different screen. Are you looking at,
blank. Oh, there it is.
do you see the modules?
Yep,
Sorry
now
about
we
that.
can.
It's supposed to show like a green image around whichever screen you're referencing. This one does not do that for some reason.
Oh, I've selected the wrong modules. Hold on.
So while you're grabbing your modules, I'm going to power up my DAC because you're all experts at that. And now what I'm going to do is I'm going to go ahead and configure it so that I'm measuring the current going into the transformer. So I'm connecting 4 to 1 lead of my multimeter. And then I run over to my terminal 1. And then I'm going to return to terminal 2. Okay. And now I'm going to go ahead and connect my multimeter, because I'm connecting at 2 points. I'm connecting across the input voltage. So I go here, here. And let me get this up a little bit because I will be using E2, so I don't want to get too tripped up. And then I'm going to be measuring a bunch of different terminals on the outputs. Now, there's a couple of different ways I can do that. I can certainly measure that with the DAC, but this might be a wonderful opportunity to use my multimeter. Because if you're going to be out in the field, if I'm going to be out in the field and I want to make quick measurements, I'm not going to be plugging in and out of my data acquisition. I'm going to just use my multimeter with those fancy probes that can easily insert into the terminals and go from there. So I'm going to measure voltage, and I'm going to go ahead and measure the voltage across terminals 3, 4. Terminal 3. And terminal 4. I'm going to configure this for my voltage, so I'm going to turn that on. And then I'm also going to have my DAC turned on. So I'm going to display E1 and I1. Those other two are, these other ones are not useful. They don't tell me any information because I'm not measuring them. And you'll notice that I've set up for AC amps on I1, and for E1, I've got AC voltage. So now I'm going to flip the switch, and this is going to disappear because it's going to go behind the screen. But I'm going to flip the switch, crank that all the way up until I get 120 more or less volts. I'm a little bit high. Let me move that to a different screen so I can do it in real time. That's really fine. Close enough for me. Show that back on the screen. Maybe I'll have it done both sides. So there's my voltage, my current. So you are now ready to do the recordings for part 7. You can see what current I have. It's 28 milliamps, right? Everybody can see it, 28 milliamps. My voltage is 120.6. And my that's my applied or primary voltage. And my output or secondary voltage is 208 volts. Okay. So go ahead and spend the next 5 or so minutes getting your data filled out for area or problem number 7. And then here's the thing. Do the values compare well are you expecting 208 volts? Remember, this is across terminals 3 and 4. Am I expecting 208 volts when I apply a nominal 120 volt? Well, I can take a look. 108 plus 76 plus 28 is approximately 104, sorry, plus 76 plus 28 is approximately 208 volts. So spend 5 minutes, go ahead and record your data. And then part 8, oops. Part 8 is to do some calculations. And so the calculations are taking a comparison between the turns ratios and then seeing what you get and then comparing that to the voltage ratios. And what I mean by that is if you look at the voltage ratio, you know that terminal 1 to 2 has a turns rate, has 120 volts. The secondary rating is 208 volts. So from M primary to M secondary should be 120 divided by 208. And so you want to compare that result and see if you get the same as the number of turns between 1 and 2 and the number of turns between 3 and 4. So go through and answer until part 9. And then let's see what you get. So I'll give you, like I said, I'll give you 5 minutes and then we'll see where we're at. But feel free to ask questions. Whatever you need, I'm here. How are you all making out? Anybody still collecting data?
I am, but I have to step away from the keyboard for just a couple minutes. I'm sorry.
Okay. Anybody other than Arthur still collecting data or calculations? I only ask because should I continue on, or
I'm all good, Paul.
how about a thumbs up from people to continue, or? All right, thanks, folks. So I'll share my screen and show you my calculations just for comparison purposes. One. All right, hopefully you can see my results. So did the calculations, first I collected all the data, and then they look pretty darn close to what I actually saw on the front plate plate or nameplate labels. And so I was pretty happy with that. And then I did the calculations. I saw the primary to secondary should have a turns ratio 1. It says 500 to 500, but we know it's going to be a turns ratio 1 because if you look at the winding 1, 2, it's nominally 120 volts. And if you apply 120 volts across that winding from terminal 5 to 6, that's that center tap application we just talked about, you're going to get about 120 volts as well. So it should be a 1-to-1 application. Whereas when you go from terminal 1 to 2 to terminal 3 to 4, that we added those all up, and that add up to 208 volts. And so when we take 120 and divide by 208, you get around 0.578, more or less. So for part 9, I would say 100%. Looks pretty good. All right, questions on that? Okay, let's move over to screen 2 again. And we're going to modify the circuit, and we're going to make it even easier because we have a fancy data acquisition device. So let's see. Let's go ahead and, well, we won't simplify this circuit. We'll simplify the next circuit. And so what I'm going to do is, first thing is I de-energize. And I noticed that if you look at the primary side of the circuit, it's exactly the same as it was before, right? We're measuring the input voltage, we're measuring the current. The only difference, instead of having this multimeter set up to measure current, is we set it up to measure, set up to measure voltage is we want to measure current. So what we're going to have to do is take this lead right here and remove it, but instead actually connect this lead to terminal 5 and this lead to terminal 6. Now, normally when you say, hey, wait a minute, Paul, don't we have to interrupt the circuit to be able to measure the current? Well, in fact, we are sort of interrupting the circuit. We're actually shorting the circuit out. If you look at the diagram, we actually connect terminals 5 and 6 directly. So we are 100% short circuiting the secondary of the transformer, which means one very important thing. When you turn on this power supply, you see how I have it almost to 100%? I'm going to switch that all the way off because I want to make sure that that's 0. And I'm going to zoom way in so that when I get some measurements, I'm going to push this transformer as easy as I can. All right. So I'm going to bring up this value over here. I've got my transformer shorted. Now I'm going to flip the switch, and this is perfectly okay. I can do that now because it doesn't really cause me any agita. And I'm going to slowly turn that up, and I'm going to do that off screen because you can't necessarily, I can't have both at the same time. I'm going to ever so slowly turn that up until I get 0.2 amps. Oops, I'm measuring the wrong. I'm measuring the wrong current. Hold on. Why was it not going up more? Because this is on voltage. I guess the meter is not smart enough to know that I shorted it out. So let's go current. Let's try that again. Oop. Measure that way. All right. So power switch is on, zoom way in again. Now I'm going to measure and turn up my current slowly. Whoops, this thing is really goofy. It's got a lot of lag, so. And so I'm less than 5%. And let me show you. I'm almost at 0.2 already, right? So I'm going to increment it very, very slowly again. Hopefully not as laggy as it was before. And for me, I'm going to say that that's close enough to 0.2. Okay. So I've got an applied voltage and I can see what my primary current is. And I'm going to switch over back over to here and record my secondary current, which is 0.186. Okay. All right. So go ahead and do your calculations for 11, 12, 13, and then repeat the process. But what you're going to do now is you're going to power this off, and then you're going to move your wires over to 3 and 4. And then you're going to rinse and repeat the process. So go ahead and do that. And that should get you up to step 15. So I'll give you 5 minutes to do that unless there are any questions. Any questions? All right. I'll give you 5 minutes to go ahead and crank that out. All right, I can get a thumbs up if people are ready to proceed to the next last part. Just about everybody. Okay. So let me go ahead and share my screen and show you. And again, I did this lab earlier, so my results obviously will look a little bit different depending on the voltage that I specified. But here's what I got. So you can see here are my primary, secondary currents. And then my ratio, I almost got a ratio of 1, right? 1.005, let's call that 1. And is it the same as the voltage ratio? Yes, it is, right? Because the voltage ratio is NP over NS. And this is the inverse of that. Well, 1 over 1 is still the same thing as 1. So I'm getting pretty well or pretty much the same result. Then I did it for the second case where I got the second value, and now I got the same primary current, but the secondary current was square root of 3 less than that, right? And if you remember the voltage ratio, that one was 0.58. What did I have? 0.58, 0.578. Well, if I take the inverse of 0.578, I'm going to get the square root of 3. And then when I compare these two, 0.212 divided by 0.122 is the square root of 3. Let's take a look at that. Let's see. I got to switch my sharing here of my screen. Tell me when you can see MATLAB, please. Oh, it's not selected. Let's try that again. Can you all see the MATLAB screen? So the current I measured on the secondary was 0.122. The current on the primary is 0.212. When I divide those, I get that value. But remember, that's I secondary to I primary, right? That has to be the inverse of that if I want to compare. So I'm going to do 0.212 divided by 0.122. And I got 1.73, which is the square root of 3. And then if you compare that to the 0.578, this is the 0.578, but that's primary voltage to secondary voltage. Remember, it is primary current. It's the opposite would be secondary current to primary current, or the other way around, right? Because we went 208 to we went from 120 to 208. That's how we got the 0.575. Now we have to do it the opposite, which we have to do the 0.212 over to 0.122, and that's how we get those values. So it's the inverse of the voltage ratio, and that's confirmed because it's the inverse of this 0.575. All right, any questions on turns ratios? Because we just proved, right, by connecting this thing, that the turns ratio is proportional to the primary voltage over the secondary voltage, and it's proportional to the secondary current over the primary current. And so that's how we get those values to work out. All right, let me switch back to the image. All right, so the last circuit we're going to build is this circuit here. But because we have enough fidelity in our circuits, we can take out this resistor and this power supply. We can make it really easy. And then what we're going to do is we're just going to look at the degree of saturation that exists in the core. And since we have a magnetic core and we're not going to build $1 million transformer, we're going to get by with hopefully as cheap of magnetic material as we can. We're going to allow a degree of saturation for the unit. So we're going to build this circuit without this resistor and this E1 supply. All we'll have is I1, E2, and E3. So we're basically going to check for magnetic saturation by measuring this voltage, and then seeing what we end up getting. So you'll notice I said the wrong voltage. It's this voltage. So really what I'm doing is I'm trying to get the voltage drop across the resistor, which is the same thing as the current, right? So it's proportional to the current. So I'm going to actually get a measurement that's going to go I1, right, as my X parameter. And then E2 is going to be the voltage across that guy right there. And then I can tell you by saturation what I end up getting. All right. So here's how I'm going to set that up. So let me switch my screen over to screen 2. Get rid of MATLAB. Turn the power supply. Well, power supply, I turned it off. And I'm going to delete those wires. just because I've got enough and I've made enough changes that I don't want to confuse myself. And now I'm going to measure the field current or the excitation current, which goes from here into terminal 6, which you can see is over here. I'll delete this wire because I'm not using it currently. Delete that wire. And then terminal 9 is going to go from here and it's going to return back to the neutral. So that's the way that I'm going to measure current. Now I'm going to use E2 to measure the voltage across terminals 6 and 9. Here's 6. Here's 9. And then I'm going to also measure the voltage across terminals 4 and 8. And that's going to be done on E3. Oops. Let's see, that's terminal 4. And terminal 8. And I'm going to turn off the multimeter because I don't need it. I'm going to bring up my data acquisition. I'm going to try to minimize this because, well, actually, yeah, I'm going to minimize this and I'll show you why I want to do that in a minute. So we don't have to worry too much about the wiring. We think we have it. Now what I want to do is I want to have I1, E2, and E3 measured. So I have I1, E2, oops, E2, and E3. And those are both already configured in AC voltages, so I don't have to worry about that. My current is set up in AC amps, so I'm good to measure that. So here's my configuration. Now I can go ahead and use my measuring date tool for my data table. And I'm going to go ahead and I'm going to configure it. Right? So I'm going to go ahead and configure. Where's my configure here? Board settings, here we go. So I'm going to go ahead and measure E2, E3, and I1. Click OK. Now I have the 3 parameters I'm going to measure. And I'm going to go back to this screen here, and I'm going to zoom way in because, again, I want to have the best level of control that I can have on my power supply. I'm going to start it really low, and I'm going to turn this up at about 10% intervals all the way till I get to the top. Well, 10% is here, 10, 20, 30, 40, 50, 60, 70, 80. But I'm also going to check and see what my current levels look like so that I'm getting about 10%. So just because I get a nominal 10% that's shown on the dial, that doesn't actually mean that I'm going to get 10%. Stop doing that, sorry. It doesn't necessarily, of course. It's like it's trying, Word is trying to outsmart me, or Windows is trying to outsmart me. See if I can back up. Okay. So now I'm ready to turn on the power supply. And I'm going to turn it up. Well, let's take a measurement at 0. Oh, I fell asleep. There we go. Let's take a measurement at 0. So I'm going to record the data. So I'm going to select and record. Now I'm going to turn it up to about 10%. Okay. And the 10% size is, close enough for here. You could break it down so that when you get the 10%, it's 10% of the voltage drop across 6 to 9. So the voltage drop across the terminal 6 to 9. What is the 6 to 9? Uh-oh. Sorry. So terminal 6 to 9 goes from 0 to 60 volts. So I got to actually take that down a little bit, right? Because I want to go in evenly spaced intervals. So if I'm going to do that in 10 steps, I should be around 6 volts for my primary. I'm actually at 12.19. So too much. So even though I only moved it 10%, I'm getting too big of a jump. So let's bring that down until we hit about 0.6 volts. Close enough for me. I'm going to hit record. Okay. Now I'm going to raise this up till I get around 12 volts. Close enough. I'm going to hit the record. Continuing on, now I'm going to go to 18 volts. Again, we're not building a piano, so I don't have to go 18.00. I just have to get ballpark, because if you were going to sit here and get exactly the numbers, you'd spend 8 years trying to do this lab. So as long as we're within, you know, a volt or so of nominal, that's fine. Now we're going to 24. Again, close enough. Hit record. 30. Okay. Now, one thing to note is, remember, when I was at 6 volts and when I was at 12 volts, I was right about 10% knob position, right? So that would indicate that I was actually moving 20% up. You know what I mean? If I went up the 20%. Now, if I look over here, I'm getting close to 30%, and this is what I want that to be, 30, you know what I mean? The approximate. So I'm starting to get closer and closer. So let's go ahead and get to our 36 number. Again, that's close enough. Continuing on, we're going to do 42. Right? Hit record. 48. Good enough. 54. Again, we're close enough there. Now we're going to go to 60. Again, close enough. 66. $70. Best I can do. Move this up a little bit. 76. Good enough. 82. 88. 94. 100. Wow, perfect. Just get lucky every once in a while. 106. 112. 118. And my last one is, as far as I can go, 124.6. Now I'm going to immediately kill the power, because in the real world, that transformer is, let me bring it up over here. That transformer between terminals 6 and 9 is only rated for 60 volts. So I actually pushed it to 124 volts. So I'm way over its voltage rating. But that's okay, as long as I don't try to overdrive it too much. Usually I can handle a bit of an overvoltage, especially for low voltage systems. And now I'm going to go ahead and look at my data. Well, I said 10 points, but I actually took over 20 points. And the reason I took over 20 points is because if I was going in 6-volt intervals, I would have stopped at 60. But I actually went all the way to 120 or 124, so I overshot it a little bit. But I wanted to get more data points. And the reason why I want to get more data points is I'm going to export this data. And we'll call it EET321 Lab. Is this 3? I think it's Lab 3. Now I'm going to open this location, which should be in the downloads folder. Yes, it is. Now I'm going to bring up Excel and start a new Excel by opening the data. So I'm going to open under downloads. Where's downloads? Browse it over here. And not shown. That's because it's looking for Excel files. What I'd like to do is I would like to look under all files, and the one over here is a text file. So I click open, and it's going to be the comma limited one once it tells me what it's doing. Finish it. And now I have E2, E3, and my current I. So now I want to go ahead and plot I versus E2. So I'm going to select those two columns. And the way that you select the two columns is you drag and drop, and then you hold the control button to move over to this character, this other field here. And now I'm going to insert a plot. And it's going to be an XY scatter chart plot, and it's going to be smooth. But this right here has current on the Y axis, and this one's on the X axis. The driving value is the current, and the output voltage is just what ends up happening. So I'm going to go ahead and select the data, and I'm going to swap my X and Y. So you can see my X values are going to be all these A's. A1, which is the voltages here. So I'm going to change that to be my currents. And then I'm going to change my Y values to be the voltage. I click OK. Click OK. And what do you think? Does that show saturation or what? You can see the slope of the line here is quite a bit different than the slope here. And I can make this very sexy, right? I can say excitation current versus open circuit primary voltage. Okay. Then I can add to it. I can add. So let's see, add a chart element. I'm going to add an axis title, and I want my primary horizontal axis. I want that one to be excitation current. And I'm going to add another axis, which is my primary vertical. And that's going to be primary voltage. And that shows the saturation. If there was no saturation, this would be a perfectly straight line. But you can see, and this is interesting, that what is the nominal voltage rating of the transformer? Do you remember which windings we use? Let's bring it up so you can all see.
60 volts.
60 volts, right? Look what happens when we're at 60 volts here on the curve. We're already starting to get to the saturation point. So under its normal operation, it's starting to already saturate a little bit, not a ton, but you can see it's starting to curve a little bit here. So even to get to its nominal operation, you have to accept the fact that it's going to have some degree of saturation. And then once we start pushing over there, then we get a lot more magnetic saturation until at this point, the transformer is pretty well saturated. And look at the voltage that I have to do. I have to go from 0.1 volts to 0.2 volts to get a change of 20 volts.
You mean
Whereas to go from here to here, from 20 to 40 volts, I might have gone 1/10 of an amp. So if that was perfectly linear, what we would see is that this would be a straight line the entire way. So this shows magnetic saturation, and magnetic saturation happens here. I have a slope. I could draw straight. I got a slope here that's fairly constant, and a slope here that's fairly constant. So this would be the saturated region. Yeah, let's see if I can do it over here. And this is unsaturated region over there. Okay. So that's how you would measure and show that one. So I've been yapping a lot. Any questions on that?
For fun, can you plot that in MATLAB?
I can, but it would not be fun because, and I'll tell you why, because MATLAB is not nearly as beautiful for doing plots as Excel. So I can do plotting in Excel. I can just incorporate the data and do it that way. And if anybody, I can show you, it's actually pretty simple. Here, I'll show you. So I want to plot current versus that. So let's see. I'm going to go ahead into MATLAB. Oh, let me stop this. And I'm going to bring up MATLAB. And then I'm going to say I equals. Here's my current. And let's see how supportive that's going to be. Oh, no, it's entering it in one at a time. Let me try a different way.
Try CSV read.
Well, I'm trying to be the poor man's way to do it. So let me show you this. So let's copy. I can copy a data in here, right? So I just call that unnamed. So that's my current plot. Now I'm going to change that to say I equals unnamed. Okay, so now I just copied the data in there pretty efficiently. I'm going to do the same thing for the plot of voltage. So I'm just going to copy that in and do the same thing over here. And then I'm going to say E2 equals unnamed. Now I'm going to plot I versus E2. And got to bring that on the other screen. Sorry. There you go. So it reveals the same information, right? But what would you rather look at? This or that? Because look at the titles. Look at the axes I have. I've got values on here. I've got values on the Excel one, but it doesn't tell you what is this voltage or current. And so you can start labeling things, and that's fine. You just don't get as pretty of a plot. And then I can very easily in Excel, I can add a trend line. So if I right click it and I add a trend line, it's literally.
You're
Yeah.
not sharing your screen again.
Did it stop sharing?
No,
Mhm.
I
Weird. I only see
Says it's still
everyone's
sharing.
pictures, videos.
I'll try doing it again. It's no problem.
yeah, I can see the dotted trend line.
How's that? Can anybody else see the dotted trend line?
Yeah, I can see it.
I can see it.
Weird.
Yeah, I can
I
see it.
only see whoever's speaking.
You
Like,
might have to bring up, you might have to minimize, that's a separate window. So you might have to switch windows to actually go to the one that actually is doing the workspace, I'm guessing. But now this trend line. So you can come up with an equation, you can come up with a linear one, right? You can come up with logarithmic and it'll try to come up with an equation that represents it. So let's try the trend line again. And that's linear. Let's see if we can do a polynomial. So that's only a second order polynomial. We can go all the way up to, I think, seventh, and the seventh order polynomial looks really good. Then you can actually add it to the screen. So this is the equation for a seventh order polynomial that Excel calculated for you.
Nice.
So you probably wouldn't do that in the real world, but you can see how you can do so much more for plotting, for basic plotting in Excel than you can MATLAB. So even some of the work that I do in MATLAB, I'll just export it to Excel just to make it pretty. And that's the process that I did here for MATLAB, was copying data over. I just do it all with the variables. Okay. All right, questions on the lab, because that's pretty much, I think, the lab. All right, I will stop the video here. or pause the video, I should say. And then you guys can finish the lab, answer questions, do whatever you need to. And that's about it. So any questions before I pause the video?
Just one, I have the chart from the lab sim, but I can't remember how did you import that into Excel? Because Excel obviously doesn't want to look for any files that aren't Excel.
Yeah, so you have you've exported this data. You export it here.
Yep.
And then in Excel, when you do an open, you open the file and then you browse to wherever it is. So over here, you can see it because I changed this to all files. If you don't change that to all files, it just looks for Excel spreadsheets.
Okay, that's what it is.
Yeah, there's a lot of little subtleties to make this work, so. Okay, I will pause the recording. And you all can do yourself. So pause recording now, and then you can ask questions. Once I figure out how to find it.